Thank you for having me. I am having a great time meeting some of you and great hospitality. So it's exciting to be here. I wish I could stay longer, but I'm here tomorrow as well. So if you have any questions, comments, or anything you want to discuss, please feel free to just let me know and we'll set up a meeting. All right. Today I'm going to talk about the idea of how big galaxies are. And most of my work is in nearby universe. The furthest I go is around 0.2, but today I'm going to focus on galaxies that are extremely nearby, NGC galaxies, primarily because they're big on sky. We can look at them, we can see things in detail, and study the exact thing that's happening versus an ensemble. So the main goal of this work today that I'm going to touch upon, some little bit review, a little bit of recent work and some unpublished work, is the idea that how galaxies are evolving and growing. The simple question, how big are the galactic disks? I think that's where I want to start. And if we can learn how galaxies are being fed based on that. So let me start with a, okay, for some reason, oh, okay. So here is a beautiful picture of triangular galaxy, and when we generally think how big is a galaxy, something like this comes to our mind. We can see a beautiful disk, and although it doesn't sort of have a very solid definition of a boundary, but you could see, okay, this is background and this is what it is. That's the size of the disk. And if you look from far, it's kind of much more clear, how we can define the sizes of galaxies. But let me just pull out the next picture. So if you look at high redshift galaxies or slightly distant galaxies, you can see that there are these galaxies and so on and so forth. They are that big. Some look smaller, some look bigger, etc. One of the observations that was sort of built over decades now is the fact that galaxies look different in terms of sizes as we look far back in time. And here's the same Hubble image. Now we have better images with DIISC, but nevertheless, for the point of this discussion, we could just look at this image and we can see that the different galaxies look slightly different. So let me just run through this video, which shows that as we move slightly back in time, we do see big structures like the galaxies we see in the nearby universe. So here is a really big galaxy, about 4.95 billion years ago. And this looks like, one of the galaxies that we see in the nearby universe, nice prominent disks, spiral arms, etc. But as we move further in time, the structures tend to seem to go like smaller and more complicated, and you can see interaction between galaxies. Here's a pair where galaxies are interacting. Presumably they will merge soon, and by the time it's redshift 0-ish, there will be a much bigger galaxy, and so on and so forth. But if we look even further back, which is what we are seeing with DIISC nowadays, we don't really see galaxies, the big galaxies that we have seen today, or even at 5 billion years ago, but what we see is this kind of blobby structure. So the main idea is that the same stuff has grown to form these beautiful spiral galaxies. And somehow you need to make it grow and produce these nice, beautiful disks. So that's kind of what motivates my work. So simply put, there are many, many indirect lines of evidence that suggest that galaxy growth is constantly happening throughout time. So for example, if we look at gas in galaxies and stars in galaxies, so we can do just a census of high redshift galaxies. Don't have to look that far high up, but redshift 1 or redshift 2, what we see is that the amount of stars and amount of gas that these galaxies have, if you add them up, in today's time, the galaxies have more stars than that. So even if those galaxies had converted all their gas into stars, they would have still need more to produce the amount of stars that we see. And this sort of tells us that galaxies must have been fed more gas into their disk so that more stars could be formed. On the other hand, we also find that the amount of metals produced in these stars by the galaxy, the stars of the galaxies, about a good fraction of them are missing. They're not in the part of the galaxy that's visible to us. So there is also this question of where did these elements go? Where is the material that was formed by the previous generation of stars? So put all of that together, what people have sort of come to this conclusion is that there must be outflows that take away the metals out of the disk of the galaxy, but at the same time, well, integrated over time, there must be a significant fraction of accretion. Some of the accretion may bring back some of the metals, but overall, there's a whole lot of accretion that comes into the galaxy that helps the galaxies grow. And these indirect lines of evidence don't only come from these big, large-scale astrophysics studies, but also from small-scale studies, especially in the stellar populations around our, solar system. For example, we see radial gradients in heavy metal distribution. So essentially, the radial distribution is not consistent with something called a closed box model, which I'll describe in a minute. There is the G-dwarf problem, which again suggests that we have fewer number of stars that have heavier elements than what is predicted, because what we see is the distribution sort of flattens out a little bit. So all of these, the solution is that new gas must be coming in, bringing with it low metallicity and then diluting the gas. So hopefully this cartoon will sort of describe this slightly better. So what we have come to this conclusion is that the closed box model doesn't work, and the closed box model, let me just run this over again, is a very simple idea that you have a big cloud, it's forming stars, and as it's forming stars, the stars are generating winds and they're going supernovae, and there are metals that are produced in them sort of enrich the material. But as the material is getting enriched, the amount of gas left is very, very low. So essentially, towards the end, there was very little material to form very high metallicity stars. So you will have only a few high metallicity stars. On the other hand, the accretion different model suggests that you produce stars and you continuously pollute the gas, but as new gas is coming in, it's getting diluted. So the new generation of stars, which will be forming, will still have some metals because new gas is coming in. And just to summarize it, the two models have very different prediction in terms of the metallicity of the stars. So to conclude this, what we believe is that both inflow and outflow both goes and sort of a mixing is happening, but we wanted to understand what's driving the accretion. Just to take a sort of a break from this modeling, I wanted to share with some of you with you all, especially those who have not paid a lot of attention to the galactic cycling thing, that 50% of the metals in our galaxy actually were processed externally. So to put this in perspective, half the amount of heavier elements in my body come from a different galaxy. So does yours. So it's actually not very, hard to believe that we are made of matter that came a long time ago from a galaxy far, far away. So maybe all this is not that of a far-fetched idea. And now, coming back to the topic, how did the material get here? All right, please feel free to stop me if you have any questions in this thread. All right, so before I actually talk about this, I do want to specify a few terms that I commonly use for those of you who are not using this Oh, maybe I will probably want to motivate this first. Sorry about that. Okay, I do want to show you this because I do want to specify why this question is even hard to answer. Why can't we just look at it and see the gas coming in? This is very analogous to what we do. This is a picture of the night side of Earth, put together by one of the NASA satellites. So what we see is lights, man-made lights all over here and there, and something else sometimes. So essentially, when we're looking at galaxies, what we have is something very similar. You see the stellar bodies of the galaxies. Now, depending on what you want to ask, that map may or may not be a very good source of information. For example, if you want to ask, where do most humans live, then this might be a decent map. On the other hand, it's not entirely true because you do see a lot of lights here on the Nile, which is just boats on the Nile, so there may not be a lot of human beings there. You see wildfires in Australia. You do see North Korea pretty dark and South Korea extremely lit, although there are people in North Korea or parts of Africa. But if you want to ask where are most of the living things are, this is a pretty bad map. Oceans are pretty dark, Amazon is dark. So essentially, this is what we are trying to get. We want to ask where is the most of the gases that is feeding the galaxies. Just like this map, our map doesn't do us justice because if you're just looking at the stellar bodies of the galaxy, what we will be listing is the source from where the gas is coming from. And as a result, we have to use different techniques. So before I move on, just to wake everybody up, I do want to ask a question. I want you to guess, because there is no other way of inferring this at this point. What is the size of the gas disk of this galaxy, NGC 99? And to put it in perspective, NGC 99 is fairly similar to Milky Way. It's a pretty big disk. So I want you to guess what are the different, what could be the size. So there are different colors here. And if you have a cell phone, you can go to this link and vote for you could do it either anonymously or you can put in your name. You can vote for whichever color you think is the right answer for the size of the disk. So I'm going to let people take the link if you want. Don't have to. Okay. I'm going to turn it over there. To search. Okay. All right. In the interest of time, I'm going to move on. I'm going to give the answer a little bit later. With you waiting. Not the nicest thing to do, but nevertheless. So I want to touch upon some of the terms that I'm going to use. IGM, intergalactic medium, that's basically matter between galaxies. The circumgalactic medium, CGM, it's basically the gas that's beyond the optical disk, but still bound to the halo of a galaxy. So that could be 99.99% of the galaxy. Quasar absorption spectroscopy, which I'm going to describe a little more, is basically looking at the spectrum of background quasars to see if there are foreground clouds are there in absorption. So what we do here in quasar absorption spectroscopy is essentially the galaxy that we are interested in studying. We find a background source, which is absolutely unrelated to the galaxy, just happens to be there, and the light comes through it. All the clouds that it pierces through shows up in absorption. The good thing is that absorption allows us to probe the gas that's otherwise invisible in emission, and also we get the kinematics of gas. What we are not doing, though, is we are not doing down the barrel spectroscopy of the galaxy that we are interested in. So essentially, in this case, you could see what's coming out or coming in. In this case, you have no idea because if it's coming in, it'll be this way. If it's coming out in this way, it's perpendicular to your line of sight, and that velocity information is not good. And of course, finally, just touch upon another term called high velocity clouds. These are clouds generally seen in the Milky Way halo. They are clouds that have velocity offset from the rotating disk. It is believed that this is the mechanism. These are the clouds that are either falling into the galaxy or flowing out of the galaxy. In other galaxies, people have used the term kinematically anomalous clouds or non-rotating clouds, including us. So it's essentially the same meaning. All right.
Why do you distinguish between CGM and high velocity clouds?
Yes. High velocity.
The definition you wrote, high velocity cloud is pretty good.
High velocity cloud is part of the CGM. Not the CGM is the entire medium from edge of the galaxy to the boundary, and high velocity clouds are certain clouds that are fairly dense and can be seen in 21 centimeter, which are falling in or out. Generally, high velocity clouds go up to about 50 kpc in Milky Way. Yeah, so high velocity clouds are just few clouds, and so CGM is like the atmosphere, and high velocity clouds are like clouds in the sky.
So why can't it be a distribution at this high end of the distribution?
Oh, yes, it could be. Absolutely, it could be. The only thing is that high velocity clouds are the high density end, but on top of it, they are also very close to the galaxy. Versus 250 kiloparsec, they are within 50.
I'm just saying that if you take the general definition.
General definition of
gas
CGM.
which is bound to the this will satisfy that.
Yes.
I was wondering why you have to.
So
It's an observational distinction.
it's an observation distinction, yes. So high velocity clouds, the history is that they were seen in the 21 centimeter maps of the Milky Way, where you see these clouds that just offset. Yes, and of course, since they're so dense, quasar absorption also will show. But the only, at that time, of course, they didn't know what they were just offset, so they were not velocity. But they are part of the system. All right, coming back to the question, how did the material get here? Let's start with the outside first, from where? So I sort of motivated that already, saying that things come into the galaxy. So let's just look from outside of the galaxy to the intergalactic medium. Is there even material in the intergalactic medium to come into the galaxy and feed the galaxies? People have been actually looking at the intergalactic medium through statistical studies. This is something called the galaxy absorber cross-correlation function. The idea is very simple. If you look at quasar absorption spectroscopy, you see clouds that are part of the entire cosmic web, and you can ask the question that are these clouds related to the galaxies in the cosmic web? And this is just a correlation, but I just want to, there are different formulations, but in the simplistic formulation, what you see is the spacely ratio of the pairs of two absorbers and two galaxies that you can count, and then you divide it by the random. So if they're randomly distributed, this number is 1 minus 1, so psi is basically 0. So people have done this for a while now. What people have found is that this is work by MRI and Weber, and which shows the strength of the correlation. So if you look from an absorber, with respect to an absorber, what you find is that you do see galaxies much closer to the absorber in terms of projected distance, as well as velocity separation. So you see galaxies very close, both in velocity and in distance, when you see an absorber. You sometimes see finger of God effect as well. Chen and collaborators also did the same work, and they also found that such correlation exists. It's just a slicing this two-dimensional function into one dimension here. So that axis is where she just collapsed this axis for about 1 megaparsec and then plotted it here. And again, you see correlation for different strengths, etc. But the main thing that these surveys did was use slightly different data. This was done with arcs. So this is 21 centimeter galaxy data, and this was optical galaxy data. So they knew about emission line and absorption line, but they didn't have any information on the 21 centimeter content. This is a reverse.
What are we supposed to see on the left-hand plot?
This one.
The left-hand side.
So this part. Oh, yeah. So this is the strength of the correlation. So this function is that. So essentially, that's the strength. So this question is, if you see a galaxy, what are the chances of finding an absorber at these distances and these line of sight velocity from the absorber? So essentially, if it's a really high number, then your chances of finding it very high. If it goes to like 0 or 1 over here, then it's
yeah, but I can see bunches of blue.
Yeah, so that's the
means
finger.
that-
Yes, that's the finger of the artifact, which means that since all these calculations assume a linear flow, the Hubble flow, but then you have these peculiar velocities in structures. So sometimes things clump up. So it's the result of that. It's not a real distribution, but it's because the line of sight goes through structures. Either it could be a filament or a group or a cluster where galaxies show a bigger
what I'm
velocity.
confused by, what I'm worried about is that you have an excess, a few megaparsec, let's say, and something in the small velocity separation. But you also have a big excess at 10 in that vertical scale.
Yeah.
So that means you have some other
Basically,
filament or some other
700
cluster.
kilometers, that is 700 kilometers per second. So that internal velocity is not corrected, it is close to 0. So what you see in that axis is basically velocity dispersion.
Up to 700 kilometers.
Let's say I am just taking Hubble constant of 70, 10 megaparsec, or 69 or whatever.
Okay, please continue.
Yeah.
Sort
Yeah,
of my
so this is not real. It's because of the velocity distribution of peculiar velocity, but this is hopefully real. This finger
side
of
there is an
Prof.
incomplete. So that side is complete coverage because given a galaxy, observers are uniformly distributed in the velocity space. Here you have a sampling problem because you need to have a background that is correct.
Yeah, sometimes you have a sampling problem.
So this part is incomplete because of that.
Yeah, we can discuss it.
So you ideally would like to see an ellipse,
Yes,
which will be lit, but
which
here,
are all
because of
smaller
very low
and smaller.
redshift, you are actually seeing large velocity.
All right. Okay. So this was done at the point I was trying to make is this was done at different samples. So people have sort of established that the absorbers are not randomly distributed with respect to galaxies, but they are correlated with galaxies. So recently, what I did is combine all that, take a sample of galaxies where we have data on 21 centimeter and optical, and then do the same analysis. And again, what we find is this is the strength of the extra correlation, and this is as a function of line of sight velocity. And what we find is that different samples show different strengths of correlation. The alpha, which is a 21 centimeter survey, galaxies from alpha shows the strongest correlation, meaning that if you pick a galaxy that is H1 rich within its ISM, which is about 20 kiloparsec maybe in radius, even if you look very far in terms of velocity, and there is also a plot that shows projected distance, you do see a very strong correlation. The correlation is next strongest for emission line, then blue galaxies, and then all the galaxies.
So what is your observer?
I'm sorry, absorbers? These are line alpha H1 absorbers.
What is the limit? because you showed in the previous talk.
Yeah, so this was done till 13.5 column density. Yeah, good question. All right. So the main essence is that the galaxies that have gas today and have presumably large disks, they are surrounded by intergalactic medium that also has a lot of gas. So that sort of gives credence to our idea that the intergalactic medium might be feeding these galaxies. Maybe very slowly, but there is material in the intergalactic medium around these galaxies to support the disk growth and star formation. So now let's want to zoom a little closer to the galaxy. Now that we have established that the intergalactic medium has material, we want to see how the circumgalactic medium looks. So that's the gas within the halo, but much further from the disk. People have studied the circumgalactic medium quite a lot in the last decade, thanks to COS and other surveys, COS-based surveys and other surveys. There is a lot of points. This is a review by Tomlinson et al. And all the surveys are marked here. But essentially, one of the things that I want to stress is, let me just first talk about the axis. Here is the distance, so that's the galactocentric radius. How far are you looking from the galaxy? So disk will be probably up till here, and then this is all in the halo. And this is the strength of the H1 Lyman alpha line. So this is much stronger, much weaker, and so on and so forth. The data don't have error bars because the errors are very, very small. The size of the point is much bigger. So essentially that's why they don't have error bars. But we do see a lot of dispersion, which means that it's something intrinsic. It's not something to do with our bad data. But intrinsically, if you poke holes to the galaxy, sometimes you see something very strong, sometimes you don't. And I want to explore that a little further with the COS gas survey, which is now almost about 10 years old. Nevertheless, so here is a survey that we did quasar absorption spectroscopy. So these are galaxies from the Galax Arecibo SDSS survey. As the name suggests, these galaxies have data from Galax. So we know star formation, Arecibo, we know H1 mass, SDSS, all the optical properties. And there are about 45 galaxies. We stack them into 4 bins of different ISM mass, 21 centimeter H1 mass. So this is the lowest mass, this is the highest mass. And then stack up the absorbers. And what we see is that as we go to galaxies that have low H1 mass, forgot to mention, all of them have same stellar mass. They're like Milky Way type galaxies between 10 to 11 solar masses. Just the H1 mass is different. So if we see for low H1 mass, the absorption is weak. As we go to high H1 mass within the disk, even at the CGM, which is 10 times further than the ISM, we still see a lot of gas. So that's the observation, and the interpretation of this, what we believe is something in terms of the covering fraction of the gas. So we believe that these galaxies with less amount of ISM has clouds, but they are very sparsely distributed. Then you go to galaxies with lots of cold clouds in their CGM. And finally, the ones with a lot of H1 in their disk most likely have a lot of clouds in their circumgalactic. All right. So this was outer disk.
What is F Lyman for peak there? What is F Lyman for peak value?
Oh, so what is the covering fraction? So we like empty, what is the? So this is all stacking up. So some lines are saturated and some are maybe non-detections. So we cannot really derive column density. So peak depth is like how far down it goes till the touches zero. The inverse of this is all right. So quickly, I want to summarize the two things that we talked about. We talked about intergalactic medium having large gas reservoirs near gas-rich galaxies, and we also talked about that the gas-rich galaxies have a circumgalactic medium, which is rich in gas clouds, neutral gas clouds. Right? The last minute, here.
I have a question in your previous slide. The one before, yeah. So you're saying that this is because of covering fraction. You can directly calculate. You don't need to infer whether covering fraction is large. You can directly calculate, right, for those subsamples.
Yeah, so we have.
But you did not mention that.
Yeah, so we have covering fraction from.
And do you see that it is increasing? Or?
Yes. So, so you could do covering fraction just by the number statistics.
Yes.
Yes. So there is also, you see. So for example, this is 100% detection, and this is.
Or 13.5-ish. What is the threshold?
What is the
threshold for the
detection? I think it was almost close to 14, 13.9 or something. Yes. But all of these were detections and they were much higher, like 14 point something to be.
Okay.
All right. So now I wanted to talk a little bit about this very, very close to the DIISC galaxy as we're moving inwards. This is work in progress, so feel free to stop me and ask questions. This is called the DIISC survey. So the name is Deciphering the Interplay between ISM, stars, and CGM, kind of self-explanatory. But the idea is that we want to look into these very nearby systems, connect how the CGM is behaving to how the gas disk is behaving and to the stars. So as a result, we have many sub sort of groups of this survey, and some of it we already have data for, others are coming in. So cost data is here, BLA and UV and H alpha is here. So that's kind of what I'm going to talk about a little bit. Just a shout out to people in the team. We've been working hard, and we have we're open to future collaborations. So if you have any ideas or interest in joining the team, let me know. All right. Just to give you a schematic idea, so this is just a schematic of our galaxy. The optical disk is generally that big. Then you have your H1 disk that's seen in 21 centimeter, much bigger. But our sightlines go around the galaxy to much large distances. For each sightline, we have a different galaxy, but this is just a schematic to put everything on the same plot. So please remember that we don't have one galaxy and many sightlines, but we have many galaxies and one sightline per galaxy. All right. Without describing a lot about the survey, I want to actually touch upon some of the results because we're running out of time, and I want to just give you a taste of what we have. So here is one of our sample galaxies, NGC 988. Unfortunately, the picture is not very pretty. There's a foreground star. Limited. The blue contours are 21 centimeter H1. The same H1 gives us the kinematic map over here. You can see how it's rotating towards us, moving away. There's some inconsistency here, which is also interesting, but for another time. And then you can look at the quasar over there. You could see different lines. We use one of the metal lines to find the velocity of the gas at that position. And let me show you over here. So what I'm going to do now, which is generally very difficult to do for high redshift galaxies or higher redshift galaxies, is that we can actually trace the kinematics of the gas from the center of the galaxy out to the H1 disk, very easily, of course. But then we can see what the gas over here is doing. So let me just do that. So that's the H1 disk, and the quasar sightline is rotating at that velocity over here, which is about like 7 kilometers off from the tip of this disk. gas. In fact, we are also modeling the data with the tilted ring, and this turnover is consistent with the work. So maybe it is consistent, the gas is rotating with this.
How do you understand 300 km per second? Such an absorption is
This
very
one?
broad, yeah.
This is saturated.
Even then, saturated at 0.5.
This is not the final spectrum. I apologize for it. It's a calibration error. So the baseline wasn't, the zero pointing was off, of course, but now we have filled it up. So the model is fine and the numbers are fine, but it was plotted on the wrong data. So it basically, so it's not an actual offset, it should be zero.
Background suppression. And you believe that C2 detection is firm?
Yes, yeah, I mean, I have not shown it here, but there is associated South silicon, silicon 2, etc. to confirm that. So we did it for many, many, many galaxies. And this brings me to the answer of the question, which is what I asked here, people. So let me see if I have answers for you folks. Okay. All right, we have a split. Okay, oh, I think yellow wins and then orange and green. All right, let's see. Yellow, orange, green, I have to remember that.
But you never told us how, what is the length scale, right?
You have to guess it from the disk.
You have to guess it from the distance,
Yes.
but if you want to
All of them will be
Fix
correct because she's not going to tell us what is the H1 mass limit up to which the curve is down. It's okay.
that's great. Yeah. Well, just to give you an idea, that's probably 30, that's probably 70, that's around 120, 160, 210 kbc. All right, and this is around 20. Okay, let me just show you the data first. So that's the galaxy over here. So I put the optical galaxy here. The H1 disk is that big. If you see in 21 centimeters, that's what you see. The quasar is right there. It's at 158 kbc away. And what I find is that I see a very strong absorption exactly at the same velocity as the tip of the disk over here. So I color-coded over here, so this part. So the velocity is color-coded. Velocity of the absorption is color-coded just to help your eye. It's also color-coded here over here. So you can see that it's pretty much the same velocity as you see at the edge of the disk. And this happens for almost all the galaxies that we have. We always find co-rotating component almost always, which match the size of the disk. So the quasar that I showed, it's right here, orange, the answer. To be honest, I don't know if it extends beyond because I don't have a quasar, but at least I know it extends here. And I want people to sort of, to appreciate that what we are seeing in terms of a disk of a galaxy is essentially really the tip of the iceberg. All this gas, which is extremely low column density. So I agree that it's probably not enough mass for it. At least one of the systems we calculated, it could be at most like 12% of the H1 mass of the galaxy. But still, this is an incredible way of understanding how gas might be coming in, because otherwise, if there is nothing there, it would be extremely difficult to feed the disk. All right. And such big disks, although have not been discussed a lot in observation because we haven't sort of connected the gas directly to the rotating disk, gas disk, That's not easy to do, but such things are very commonly seen in simulations. I'm going to put a very old one because I just wanted to stress that this idea has been there for more than 10 years, where the fire, before, this is fire where you can see, but even before that, has Stewart sort of shown this stuff, and you can see that they have almost a disk that is 200 kiloparsec. Since I'm almost out of time, I do want to quickly mention a few interesting things so that people, if you're interested, you can talk to me about these things. This is one of my galaxies. This is M61. It has been studied to death, but there's still more surprises. So we have a quasar that falls, that goes through the H1 21 centimeter disk over here. So that's an extremely wonderful piece of information. Now we know the kinematics of the gas in disk, so from the imaging, so we can figure it out from our VLN maps. It's about 70 kilometers. If you look at absorption, the H1 is very, very saturated. It's hard to see, but in metal lines, I'm showing 3 different metals. There are other metal lines as well. What you could see is you can easily see the ISM very, very strong with metals. You also see something which is 345 kilometers per second offset from the ISM. Something like this, what we see in Milky Way ISM, well, Milky Way halo, through a quasar, we call it high velocity cloud. So essentially, by the observational definition, this is a high velocity cloud. Now, what we think is this happening is that this cloud, we think it's an infalling cloud. It could be from a fountain that came out of the galaxy and then falling back, because at this point, there is nothing happening in terms of star formation, and this galaxy is not extremely star forming for it to shoot something out so far that at this projection, it's 345 kilometers. So what we believe, please stop me the argument, I can expand on that. But essentially, it's not star forming enough to throw something out at that velocity. So we believe that this must be influenced cloud. And if, simplistically, if you just leave a cloud in a potential of this magnitude, it will reach that kind of velocities. So we think that maybe these things are recycling of material. They're metal rich, but they're falling back into the galaxy. I'll also show another example, but this time a probable outflow. This is M100. Again, it's the H1 map. This is the optical map. And this is the channel maps. For those who are familiar with radio, what I'm going to do is just run you through a channel map and show you a cloud at the position of the arrow, which is over here, which is not co-rotated. So at the rotational velocity, you can see the material over here. However, if you look here, something will pop up. So this cloud is, again, by definition, will be one of those anomalous velocity clouds or high velocity clouds. And what we believe is the spectrum of this cloud, because it's coincident with FUV bright region and an H alpha bright region. It's the same region, which is FUV and H alpha bright. We think that this might be a cloud that is being pushed out by the star forming region. We can't be 100% sure till we get spectroscopy of the H2 region and see this in absorption. But at least that seems to be the most reasonable scenario at this point. So there are all these hidden gems in the data that you're finding, but for the interest of time, just gonna leave it to that. But I'm gonna just kind of end up with this idea that how galaxies are being fed. Maybe I'll skip this, but this is my bragging image. So I do want to spend a minute. If you can't see this because the beam is so small, very rarely I have been working with data that's so good. So that's the H1 21 centimeter map of this Galaxy NGC 3344. Interestingly, this is an XUV disk galaxy, extended UV disk, which means that there is more UV outside of the optical, which basically the UV size is bigger than the optical size. And there's all this H1. There's a detailed paper by my student, Mansi Kadave. If you're interested, you can take a look. But essentially, now we are getting very high resolution VLA data with B, C, and D configurations. So we can actually do detailed mapping of what the gas is doing. All right. Anyway, so the point is that if you have such kind of data, you can do really good disk modeling, and then you can see that all the CGM gas that we think is the extended disk, at least in the inner parts, they are moving inwards. So here is a modeled point of the same data that I showed before as a function of galactocentric radius. But as you can see that there is this positive means radially inwards, the negative means radially outwards. And what we can see is that at the truncation radius, which is the radius of the UV disk, where the star formation has halted, we see that there is gas falling into the disk at that point. So we do see that stuff, all this extended disk is sort of helping feed the galaxy in this case. Interestingly, we also see a warp just starting at the truncation radius. So the feeding mechanism might be related to something that has caused the warp in the disk. All right, the modeling can also help us identify non-co-rotating clouds because you have a model of co-rotation and then you can just subtract the data and get some images of non-co-rotating clouds. This is very preliminary. I'm not gonna, 100% state that these are real, all of them are real, especially the ones in the outskirts, but inwards, we are very confident that these are real non-co-rotating clouds. All right, so just to end, I think in certain cases, what we are seeing is this fountain model, which I just touched upon, especially in some of the galaxies that we have data for. We're seeing the stuff might have come out very hot. We don't have access to this information at this time, but what we're seeing is as this material, this metal-rich material, is coming back because it doesn't have escape velocity and falling back into the galaxy, we are picking it up as high velocity clouds. And that could be one of the other methods. Of course, there's a large extended disk that's also falling inwards. That's there for every galaxy, but in addition, there could be these clouds that are recycling the material, and that might help bring some of the gas from the circumgalactic medium, which cools down. So something less might come out, it might grow here and come back down. So this is a model described in detail by Filippo Petronelli, and at least our preliminary data for some of the systems are consistent with this kind of model. All right, I'm almost out of time. I think I will stop here and let me just quickly shout out to my team. Some of them are graduating. If you're looking for postdocs, think of these people. Mansi is doing a lot of UV work. Tyler is an expert in laser absorption spectroscopy, etc. These people have worked very hard on this, so just wanted to give them a shout out. Anyways, there's the summary. At the end, I do want to mention that we're just getting started, but it'll be exciting time with SKA. Then we have a whole lot of maps with GMT, which will give us a lot of information on nearby galaxies and sometimes even further. We can extend this further. So essentially, the future is bright and there's a lot of data to reduce. I'll stop here. Thank you.
Question? Nice to know you. Just go back one slide, two slides. Besides the pictures. So why do you have to
For the comment, what is the sort of verification? It has, can you confirm if there is starburst something that's thrown out the gas? Can't they just condensing from the environment and falling in?
Yeah, so there is not 100% like certainty, but this is metal rich. So that's the thing. So when we see the exact metallicity is hard to say, primarily because the line is saturated and it's merged with the ISM. But at least from one end, we could say that it's around, I mean, clearly it's not a DLA because it doesn't have a damping ring. The high velocity cloud is not a DLA. So, and then we have good measurements on the metals. So we think the metallicity of the high velocity cloud should be of the order of a solar or maybe even more. So I cannot rule out that it's not the circumgalactic medium gas just condensing, but the metallicity seems a little too high. So that's why the whole idea of this.
Your team trying to correlate this clouds that are falling. So essentially the fountain cycle time scales. Have you tried to see it from semi-stellar populations something? Anyway, there's a lot of degeneracies in that, so I can't get one of the debate of that. But identify a potential starburst in the early phase which could have given rise to the cycle or any constraint in the time scale?
Yeah, we're trying to do that. We're trying to do the stellar population of these galaxies now that we have resolved mass. We're also trying to see young star supernova remnants. This is just getting started, so we're pretty much in the nascent stage. Yeah.
I wanted to know about the population of the DISC group that you're doing. I guess you don't have aliens in there. If not,
yes. There. Okay. So when we selected,
people throw the AGNs and then work with the star planning galaxies. I focus on the AGNs.
So we do have 3 sequences.
3 sequences.
Yeah, one is just on the boundary of the BPT diagram where you define sequence. So depending on how stringent you are, they may not be sequence, but one of them is.
The reason is all this recycling business that you're trying to get at from this body of work is mostly driven by star formation driven events. Is that right? Or are you also think that some aging component can also improve?
So naively, we were thinking of star formation, but recent studies show that AGN could be a very important factor, if not in the distribution of metal, but in their ionization and mixing and circulation pattern for sure. So yeah, but having said that, even if the AGN is not active today, it could have done like contributed.
So the second hub, that is when you said that the discs are really large, and that is entirely based on having the same size, same sign for the absorption and the disk rotation, right? So then, and then my question is like, what fraction of the cases you saw this? It's 100.
Yes, very good. So honestly, all I have is one cloud is rotating at the same place. And I don't know what's in between. So this is like, the jump is because in all the galaxies that I have measurements for, so this is 34 galaxies and 2 of them did not have any Lyman alpha because they're cluster galaxies, including one M100. But for the other galaxies where I have Lyman alpha detection and I have a measurement there, what I find is that all of them have a co-rotating cloud. So it's, think of it like 30 out of 30. So essentially that gives me about a very high covering fraction. So I honestly, it's not probably the right thing to say a disk. It could be like a flaring of a disk and a bigger cylinder, but it can be like a tower also. So it's probably a more thicker disk-like structure, not the thin disk that you see for the stars. But the covering fraction is very high. Like at our level, it's 100%.
Yeah, 30 out of 30 is showing the same.
Same.
Yeah, well, because if it is only a handful, then it could be just like.
It could be just random, yeah. That's
And if, in your first half, when you showed that H1 mass and your Lyman alpha strength, did you control the impact parameter? You said that stellar mass are the same.
Yeah, we did control the impact parameter. Then, of course, we had to split the sample into 2 impact parameter bins and then smaller. Yeah, so you know, right? The big sample of 40 can only give you so much. Yeah, then we see then we see for every impact parameter, the higher H1 mass had bigger coverage. So, like, essentially, yeah, I had 40, so I could only make 4 subsamples. So I divided into 2 subsamples, one close to the disk, one away from the disk, a high impact parameter, and one high H1 mass, one low H1 mass. And there, the low H1 mass had low compared to high at every impact.
Have any conservative or even a guess for the total mass contained
In the outer disk? Yes. So assuming they're in photoionization equilibrium, we calculated a mass, and on an average, it's about 8 to 12% of the mass, the H1 mass of the galaxy.
In terms of the problem that you had stated earlier, current mass, stellar mass is much higher than
Yes.
mass. So where does this?
Very good question. I should put it in the set. So essentially, it doesn't tell us about where does the mass come from. Okay, so it's not this much mass cannot really sustain star formation, but it's like saying this is the pathway, because the fact that if you have to feed the disk, you need to have material outside that's feeding in. Right? Think of it, it's like a highway. Right now, there are some number of trucks in it and bringing food into the cities, but that's not enough to feed the city. But this is a pathway. So essentially, although we do not have it's just 10%, although that's not enough, but that's kind of comparable to the star formation. It's actually much more than if I take a radial velocity of few 1 or 2 or 3, whatever is the number for the galaxy, and then the radial thing, it actually comes out to the very similar number for these galaxies, about 1 or 2 solar masses per year. Most of these galaxies also have star formation rate of 1 or 2 solar masses per year. So essentially, we think that this is a channel through which CGM might be condensing. I didn't show you some slides, but we have some evidence that as you go closer to the disk, you see condensation, that the gas becoming more dense and more cool, and then you see more neutral species. So what we believe is that CGM might be condensing into cooler clumps as we move closer to the disk, and then this big disk will have some radial.
Assuming that you are correct in saying that in the very outskirts at 200 kbc you are getting co-rotating gas, how much dark matter mass would you then have within this? Because you're effectively building a rotation curve out to 200 kbc that is not falling. So you are increasing the mass of the galaxy by what factor of 2 or 3, I think?
So that was a point of contention, and also.
So what I don't understand, why is the problem?
So if you you would eventually at some point of time expect the rotation curve to start falling.
Not at 100 plus.
To 200, she has 200 kiloparsecs.
So yeah.
So the question you have to ask is that's what I am also worried.
Yeah.
200 kiloparsec is how it relates to the virial radius. But these
Yeah,
are
exactly.
very massive galaxies. If 300 kiloparsec is virial radius, you're okay.
Yeah, I mean,
I don't know what is the
Yeah, the virial radius is 300-ish. Yeah. So this is.
The only problem what you have in mind is the stability. Why this guy is still keeping the disk shape? Because the only thing you would say is that there is an ionization, because of which you are not seeing. But why instabilities like Tumble or any of those things didn't come, and why they are going up to 100 kiloparsec? Because if you say warps, we are already talking about some instability. Why?
But the warps can also be.
There is a problem. Okay, let her answer whatever she wants. What do you think? I mean, this question is relevant.
Yeah. So simulations, you could have you do have, so there could be minor instabilities and you could have warps, and I'm actually saying there could be warps, actually, I do see that. But in simulations, you are producing such disks of that sizes. So not out to the virial radius, but at least like half the size of the virial radius. Although I do agree that if I'm saying that I'm bringing the gas into it and it has an angular momentum so much in the outskirts, and maybe I'm answering a different question, is showing problems, but nevertheless, I always ask theorists this question, so maybe it's open to everyone. So yeah, so then I do have the angular momentum problem, that somehow I have to reduce the angular momentum of this gas and get it to 20 kiloparsec, which is a bigger thing.
No,
But
not just
recently-
that, because if you take the angular momentum that you would get in a halo, it's only 5% of what you require for rotational support. So to form a rotating disk, you need to collapse by factors of 10. So how do you find a rotating disk at 200 kiloparsec? If it's rotating.
Yeah.
If it just cool down on some axis and not rotating, then it's
That's right.
But that's weird.
Huh?
That would be weird.
No.
You have a collapse
See,
disk.
if you don't ask me, in
I'm
the
not
simulation, there is a answer to it. This is what some of our younger colleagues believe. Accretion is towards this thing. So if you have an angular accretion
that
like
is a
this, then
different
you can
answer.
support
If
us.
it's a rotating
This you want.
disk,
I don't agree with it, but that is what you ask any of the graduate students working on quasar absorption line nowadays. They say that accretion along the disk and
Why should it
ejection
accrete along
perpendicular to
the
the disk. So this can give you this.
No, why would it accrete along the disk?
No, but I don't know. Tomlinson said everybody believes now.
But if it's
I mean,
rotating, there's a
that-
problem. What is
The mass has to be larger to support that kind
No,
of.
no, because you won't have that angular momentum unless
Mass
you
is
come
not a
from
problem.
far away.
You will have mass. Because mass will give you, see, any velocity dispersion you need anyway, even if you put it going around the circle.
So we are more discussing than you.
No, I think, I mean, it's the simulators that have come up with this thing, but they do have this like accretion along filaments, and the accreting gas comes in that direction. But now there's this recent paper by Fire where they have some complicated term for it, the realization. Like, okay, I don't want to state what incorrectly what they're saying, but yeah, so they have this thing that the gas collapses at a certain virialization temperature into this disk. So
Cold mode accretion.
it's not exactly cold mode, yeah, but it's kind of similar. But the thing is like virialized outside, and then to inside there's some virialization radius that they find. Since this is not my work and it's very recent, I have not read the paper in detail. I don't want to sort of comment.
One question.
Can we go back to the slide of high velocity clouds and system?
Definitely.
Yeah, so I got the three pictures, like the first, second, and the last one. But like the two graphs are there, right? Yeah, that one. So is that related to the data we're getting from the three pictures?
Can you just repeat the last part?
Like the graphs, like the graph we're getting, where we're plotting the graph, is that data related to the data we're getting from these pictures? Or is that?
Oh, yeah, where is it getting? Yeah, so this is from the quasar. So, this quasar, which is in optical, you can see, that's bright in UV. So if you take the spectrum in UV, this is the spectrum of the quasar, and it has these absorptions.
So
As the redshift of this.
That's the scale.
Yeah, so those two come from the HSC cos data. And this one is from this data, which is 21 centimeter. And all I have done is like take this part of the data and then just plot it as that.
No. That's some question online.
Online.
You can ask the person to say.
Yes. That's what I see.
Also, what are the components? Oh,
Can they unmute by themselves?
You can ask them.
You have to click and ask them. Just click on.
Maybe you can speak and you can tell that. Yeah.
Hello. Would be paying attention.
Yeah, that's.
Hello, why do you want me to turn to why?
They might have got now.
Then how do I?
We can just say.
Hello.
Already after.
Nilanjana, can you?
Yeah. I was thinking that in a slide where you were showing perspectives from simulations, there was one video from fire simulation. So I was wondering, what are the components shown in the video? Yeah, that one. What are the
Oh,
components
yeah.
shown here? And
It's-
does it reveal that the gas accretion and that it has a large radius, like you said, like 300 kpc or something?
Yeah, so this is just the gas content map. So the red is like very low density, and yeah, the clouds have high density. So essentially, the green is slightly higher density. I do not know the exact numbers. I'm sorry about that. But yeah, so this is just to give you an idea. This is the green stuff is probably the stuff that we could see in absorption around 10 power of 13 in column densities. But this is in density terms, so it's not exactly 1-to-1. Yeah, and the sizes are kind of similar. The diameter could be around 200 kpc for Milky Way type galaxy. Yeah. Does it answer the question?
Yeah. Thank you very much. It was very informative. Thank you.
Thanks.
Okay, I think stop here. Let's thank the speaker.
Yes.